Welcome back. Are there any questions? Now I can ask officially. But now I'm on the watch. Before I wasn't. Okay. No questions. Let me say something about the Riemannian matrix one more time, just because there's this particular funny-looking formula that I will use. So we talked about the Riemannian metric on H, but we haven't talked about the Riemannian metric on SO2 R. But you can also do that. You can define, there exists a good definition of the Riemannian metric on G, e.g. G equals SO2R, but now we don't have to restrict ourselves any longer to SO2R. We could do the same for SO3R or some other simple Lie group, connected Lie group. We can define a Riemannian metric such that the resulting metric is left invariant, i.e. dHg1 hg2 is equal to dg1 g2. So left translation doesn't change the distance. And that would be the distance function that we want to use on the group. And now you can define, using this property, you can define a function on a distance function on x equals g mod gamma discrete, but just taking the two cosets and then taking the infimum over all gamma 1, gamma 2 in gamma, distance gamma 1 g1, gamma 2 g2, and if it's such a big infimum, then you would wonder why it has the usual property of a metric that it's bigger than 0 if the two cosets are not the same. And here's where this property comes to the rescue, because we can kill one of the gammas. We can also write it as the infimum over gamma in gamma. Gamma is a group, right? So I can put this over here and then use that it's a group and write it like this. And once I've eliminated one of the gammas and I've only one left, I can say gamma is discrete, so it's closed, and no matter what I do with the simple G1 and G2 with it, I realize that this infimum is actually a minimum, because gamma is discrete and closed. And then it's easy to see that it's really a metric on the quotient space.
But you could also say that's a Riemannian metric just...
Yeah, you can also lift the Riemannian metric and then do this thing, but let me just say, suppose you have a metric on the group that has this property, then you can make that definition. Now, this definition has another nice corollary, and we mentioned it implicitly already yesterday when we talked about uniform lattices and what it makes, what really is uniform in them. So if G1, G and H, just G and H, and if G and H are G and gamma is discrete, then the distance function on X between gamma G and gamma GH is less or equal than the distance in G between the identity and H, and equality holds if D, G, identity H is small enough. That, yeah. You should think of that you get this here by multiplying sort of the coset on the left, the identity slash the element H. And then it's clear why left invariance of the original metric should give you this property. And why is it not always equal? It's not always equal because this might be huge, right? And the quotient x might be compact, so it can't be always equal. Because if x is compact, then the distance function should be bounded on x. But g may not be compact, S2 is not compact. So the distance function actually there is not bounded. So it can't be an equation all the time. And it's not an equation precisely because the gammas, if the h is large, you might use it here gamma while you don't use a gamma here. And that makes sense because our definition invokes gammas. It's rather easy to check, so let me not do it. You can ask after Gas or something to talk about this. Good, so we have this formula, and we implicitly also used it yesterday because I already talked at what happens if I multiply an element with a small element, then the distance really is small. Maybe even smaller than what I see on the right hand side here. But it's at least as small as what I see on the right hand side. If the h is smaller, then this is useful. Let me also say another stupid thing. So the way we introduce the subject, it's natural that we started talking about the gamma on the left because the gamma was acting on h, and the h then gave rise to the g somehow, and that's why the gamma was on the left, and we have an action on the right by g. Now it's clear that the left action of g on an element h in g is just gh. The right action of an element g on h needs to be the opposite way around, otherwise the non-commutativity wouldn't give rise to the correct formula. It doesn't really matter much. If you put this into the regular representation, which we also have seen, you have to again add an inverse, one more inverse. So if you act on the right but you act on functions, then you don't have the inverse. And if you act on the left but you act on functions, then you have an inverse. That's the way it works. And if Uri can now stand up. And then, no, that was a bit too quick. Anyway, part of the dynamics community believes this is too annoying. So you could also define x twiggle to be g mod gamma with gamma on the right. And then you have a right and left action on g mod gamma instead of a right action on g mod gamma. Doesn't really matter because these two things are of course equivalent, because when you have gamma g, you can map it to g inverse gamma, and then everything gets mapped to one another, and it doesn't matter. However, it matters in my setup because I defined my geodesic flow, and if I just look at the geodesic flow, it doesn't matter how I write down my element. But if I want to look at the bigger group action G on the right, then I better define it the correct way, namely with the inverse. So I should change my definition of the parametrization of the diagonal subgroup and put another inverse there. And probably this was quite enough to talk about science. So that's my correct definition of the geodesic flow. With over 2 here, then it's really correct. And the action AT acts on X. I don't write it as right G of X. I just write it with a dot. It's then the same thing as when G acts on X is X G inverse. So this is X AT inverse, and then on the right I see the inverse again appearing and killing the minus there and putting a minus here, and then it matches with what I called the geodesic flow yesterday. Theorem. Hobbes' argument. The action of A1 on any finite volume quotient S to R modulo gamma is ergodic. The proof of that we already saw in the morning in the different language, but let me repeat it, because this use of Lusin's theorem combined with the ergodic theorem that I will have to do now, this use is very, very important. It's somehow this combination of ideas can be used to prove quite a few different things, not just the ergodicity, which you could get by the unitary discussion from the morning. So let me do it, because it's worthwhile. Not so much because of the theorem, but because of the proof. Let f in L2 x mx, that's my normalized R measure, this is x, be an A1 invariant function. That means that f of x is equal to f of x A1 is equal to f of x A1 inverse, which is A minus 1. For almost every x. Today we don't want to cheat as much as yesterday. We only have this at almost every x. And what do I want to show? F is constant. Almost everywhere. Because then I have ergodicity. Ergodicity we define in terms of invariant subsets. But once you have an invariant subset, you can look at the characteristic function, and then you have this invariant function, and if this invariant function is constant, then the set was either nothing or everything. Okay? Now, what's Lusin's theorem? It says for every epsilon greater than 0, there exists a compact subset of X such that we have quite a few nice properties. So one is, the set is pretty much everything. It's not an almost everywhere set. It's not everything up to measure 0, but it's missing an epsilon portion of the space. And the second property is that when I restrict this measurable function, was L2, but it doesn't really matter for that statement. If I restrict this measurable function to my compact subset, then it's continuous. Hence uniformly continuous, because K is compact. That's sort of measure theory. we will not prove that. It's a standard fact from after defining Lebesgue integration and so on. You can also check that statement. Okay, what's the next thing, next step? Let me do it logically, which means the next step you will not understand until the end of the proof. But we define x1. It's the set of all x in x for which the limit n goes to infinity 1 over n sum j equals 0 to n minus 1. I'm taking an ergodic theorem. Characteristic function of the set k applied to x a 1 to the minus j. That limit, which exists by the ergodic theorem, now you should stop me because yesterday we have seen the ergodic theorem with the assumption of ergodicity, right? Now I'm trying to prove ergodicity, so it seems like cheating, but the ergodic theorem doesn't need the assumption of ergodicity. The limit always exists even if the system is not ergodic, but the limit may not be the constant function, may not be the integral. It's some other invariant function that we will use. So we call this maybe 1 index k bar for the averaging that happens. That's some invariant function that we don't know at all. And that's the ergodic theorem, and then I'm allowed to use the ergodic theorem if I don't say that this is constant.
Of x, right?
That, yeah, of x. Yeah, and I need to finish the definition of the set. I want this to be greater than 3/4. Greater or equal than 3/4. What is this set? This set consists of all the points that spend 3/4 of their time, so 75% of their time inside the set K. Okay. Now, there's one more information that the pointwise ergodic theorem in a non-ergodic case gives you. It's not just n invariant function. It's n invariant function whose integral happens to be the same as before the averaging. So the integral of this new function, the averaged function, is equal to the integral of the characteristic function before the averaging, which we know is by assumption greater than 1 minus epsilon. So if you know that, and you make that definition, and clearly this is between 0 and 1, you just, it's called Chebyshev inequality, right? So the trivial inequality if you integrate over a small, over a set, and you know that on the set your function is quite big, or quite small actually, because you have to do the complement, you get an inequality out of it. You have to do it for the complement of the set, but who cares? You get a nice statement out of it. So from this trivial inequality you get that the measure of the set x1 is greater than 1 minus 4 epsilon. So somehow what's missing here is 1 over that is amplifying the epsilon. But this set x1 is still really almost all of the space. Nearly all of the space, I shouldn't say almost. Nearly all of the space. Okay? Yeah, now we're more or less done. What do we want to show? We know that the function is invariant under the diagonal flow. We want to show that it's invariant under all of SL2R, because then we can say we have a transitive action. So now SL2R is generated by the upper unipotent and the lower unipotent. And if we can show that the function is invariant under the upper unipotent using n going to infinity plus infinity, then probably we can do the same with n going to minus infinity for the lower unipotent. So let me just talk about one of them. Let u minus be 1 S1 S in R, and take an element u from there. We claim that f of x u equals f of x for almost every x. So the action of the upper unipotent preserves the function. Similarly, for u plus, and this gives the theorem. Because then the function is invariant under everything. If it's invariant under everything, it's constant. That's what we wanted. Let x be in, I don't show the almost everywhere in one go. I show it up to 8 epsilon. And epsilon is arbitrary, and then I know it for almost everything. So I take x in x1 intersection x1 u inverse, say. So that means this is greater 1 minus 8 epsilon of capital X. So if I show it for all the x's in here, if I show this equation for all the x's in here, since epsilon is arbitrary, I'm done. Okay? Now I do precisely what I outlined yesterday, and the continuity will kick in a minute. X is in x1, right? That's what I said. What does this imply? This implies that 75% of all n's, 75% of all n in n have greater or equal 75%. Maybe it's 100%, I don't know. But greater or equal 75% of all n have x a 1 to the minus n in k. Well, this statement is defined, of course, by that limit expression, but that's nicer to say. And same thing for xu, right? xu is in x1. We get the same for xu a 1 to the minus n. It's also in k. Now, of course, the n's that have that statement here and the n's that have that statement here, these two sets of n's have nothing to do with each other. However, each of them is 75%, so for more than 50% of the time, both of the statements is true. So what was important about 3/4 is that it's bigger than 1/2. We get infinitely many, and that's the only thing we need, n with x a 1 to the minus n in k, x u a 1 to the minus n in k. Simultaneously. And now we finish the proof with the stupid outline from yesterday. We have f of x. F of x equals f of x a 1 to the minus n. This holds almost everywhere, right? By assumption. So I'm not losing any epsilon or whatever. I'm not losing anything by saying this holds. I have to remove an alpha.
So logically you should have removed it before the final k? Yeah.
Now this is equal to that. And on the right I have the same thing here. This is equal to that. But now I'm rewriting this in a complicated fashion. And what I see here is something that goes to the identity rather quickly, exponentially fast. I still have my definition here. So if you multiply this with the minus here, with this, with the entry here, then this entry gets multiplied with this thing. And hence, this is already small in the upper right corner, and then this fixes the diagonal entry and makes it even smaller in the upper right corner. But since this is now very close to the identity, and I'm in a compact set where I have uniform continuity, I can say that for large n this is almost the same. But since it's not changing along the way, it's the same all the way, all along. So we have shown this. To be precise, we have shown this for almost every x in x1 intersection x1 u inverse. Now you let epsilon go to 0 and you're done. We have shown it for almost every x. And then you do the same argument with n going to the other side for the opposite u. And you conclude that the function is invariant almost everywhere under all elements of SL2R, and because this is a transitive action, you conclude that the function is constant, and hence the theorem is proven. Are there any questions to this proof? Okay. So somehow these matrices with one golden diagonal and something in one of the two corners, they keep popping up. They keep being part of the discussion. And yeah, they are interesting in their own right, and for most of what will follow, we will talk about them. But before, let me remind you that in the morning we have seen a stronger statement, which I will not reprove now. Theorem, this is Moore, or corollary thereof. Actually, the A action, the A1 action, the A action is mixing. Same setting, you have x, finite volume quotient, and then you have this diagonal flow, geodesic flow, and it's mixing. Which, let me remind you, means that when you take the measure of some Borel set and you intersect it with another set which you modify by some element in the geodesic flow, the B1 is fixed, the B2 is fixed, but the t goes to plus or minus infinity, then the measure of the intersection goes to the product of the measures. The two sets become asymptotically independent, right? In probability theory, we would call this equation independent events, and two sets, of course, cannot always be independent because they might be equal, but asymptotically, they are independent. An equivalent way of stating this is in terms of matrix coefficients, of course, or in terms of inner products. So you can take a fixed function f1 and then another fixed function f2, which are composed by the geodesic flow. You let absolute value t go to infinity, and then this converges to the product of the two integrals. On the orthogonal complement of the constants, this would be 0. This is how we established it. But for general L2 functions, it would be that statement. Constants are irrelevant, right? I mean, they are constant. You just take them apart, and then you see this term, and the elements that are orthogonal to it, there you apply the theorem, and then you see that the error term, the remainder term goes to 0. So that's it. And it's also quickly checked that this is equivalent to that. I mean, you just approximate the functions with simple functions coming from characteristic functions, and then this theorem applies. That statement applies. That statement, the other direction is even easier, just take the characteristic function first. Okay. That's great. There was another topic yesterday. We talked about ergodicity, right? Fine. Now we have ergodicity. We even have mixed. But we also talked about unique ergodicity. So you should ask, what would you ask? Is it uniquely ergodic? Maybe.
Can you switch pens?
Yeah, I was thinking about the same thing. You take your job seriously. Maybe the action. You even had one from here, that's what I'm saying. Good. Maybe the action is uniquely ergodic. Well, that's wrong. No. Let me give you a nice example. This is our fundamental domain, our modular surface. Now, of course, I messed it up already by not making it in proportion, so the picture will not be nice, but never mind. Here's I, and then you take down here minus the golden mean, and then over here, well, no, minus 1 over the golden mean, and here you take the golden mean, and then you take another geodesic like this, where you have here 1 over the golden mean, and here you have minus the golden mean. And then you look at this geodesic here. And you let the errors go in both directions. And you walk around and use the two rules that I gave you yesterday, how to glue sides of the fundamental domain to each other. And you apply them to the endpoints accordingly to see which geodesics you get. You do that 4 times, and you end up back at the point where you started. So this is a periodic orbit. It just winds around in some way through the space and closes up perfectly. But once you have a single loop like that, you have an invariant measure sitting on that loop. Just a one-dimensional Lebesgue measure on that loop. So it can't be uniquely ergodic. And you have many such nice periodic orbits. They all come from quadratic number fields, real quadratic number fields, and ideal classes of them. There's a nice story attached to all of that also. But already one such example, of course, destroys that, because the back measure is ergodic, this is ergodic, because there the action is transitive. So you have 2 ergodic measures. But that would still be a nice example, right? Now let me tell you another statement. Let's chop off the cusp high up somewhere. Take it away. And now ask whether this dynamical system, where you always die if you run into the chopped off part, whether this dynamical system has invariant measures. And the answer is yes, of course, we saw already one. But we can ask whether it has a dynamical system with positive entropy. And the answer is yes. If you take that line high enough up, you can get dynamical systems with positive entropy very close to the maximal entropy. That's something to prove, but it's true. So you get lots of fractal invariant measures, where fractal really means fractal in dimension, not just closed set. So it's very fun. Of course, you might like fractals, but this orbit you should like even better than the fractal, right? So there are different levels of niceness, and a fractal invariant set measure isn't so nice as this set is. So maybe at some point we have a definition of nice in that sense. Algebraic. Maybe at some point we have a definition of an algebraic invariant measure. We will have one. Not now. Right, so there's no chance of any nice statement for the geodesic flow. Period. So let's switch the flow but remain in the same space. The horocyclic flow is the new topic. And we define U equal U minus equal to this group 1S0, 1SR. And we replace A, which we talked about before, by U. Theorem, the U action is ergodic. In fact, mixing. Whenever I don't say which measure, then I really mean the Haar measure. That's sort of the natural measure. And that's a corollary of Haar again, because actually it's not the A action that's mixing, it's the SL2R action that's mixing. And if you have a big group acting and it's mixing, then all of its closed subgroups are also mixing, just by the way the definition works. So the A action is mixing by Haar and the U action is mixing and hence ergodic by Haar. It's all the same. But that's not surprising. But we can now ask the same question that I asked here for the geodesic flow for the horocyclic flow. And in fact, Fürstenberg asked that question and answered it. And the question was natural because theorems in that direction were known before by Hedlund and so. The U action on a compact quotient x equals gamma mod out from SL to R is uniquely ergodic. Now that's a major step up, right? Because this statement tells you almost every point has an equidistributing orbit in the space. But it doesn't tell you anything about the almost every. If you give me a point from this theorem, I wouldn't be able to deduce whether the orbit equidistributes or not. So it's a nice, satisfying theorem jointly with the pointwise ergodic theorem, but not as satisfying as this, because this says every orbit equidistributes, i.e. integral from 0 to t f of x ut, I write ut for us maybe, for the unipotent flow. Maybe I should put the -1 for consistency. ds 1 over t converges to integral f over x emx for all f in ccx. No, for all x in, there's no c. It's common, right? That's equivalent to that by more or less the same discussion as yesterday. Yesterday we had a discussion for n actions, and here we have an r action. It's the same story. We need to have the pointwise ergodic theorem also holds for an r action. It's very nice, but the pointers I codifferent together with this will tell you that for all f and for all x, but this theorem tells you that for all f and for all x. Now, theorem by Nani generalizes this to non-compact motions. However, the generalization must look more interesting. And I quickly draw to you why it's more interesting. Before I do that, I need to draw you homocyclic orbits, right? When I defined the geodesic flow, I defined it in terms of following this arrow straight. And then I drew you lots of geodesic orbits, namely the geodesics in the hyperbolic plane. I should do the same for the homocyclic flow. So, and again, that's the left-right, it acts on the right. So I should first act on the standard reference vector, and then I see what the U really does. So for this vector, because it corresponds to the identity, the right action, the left action is the same anyway, so I just apply the Möbius transformation that corresponds to the 1S01 map. So I translate by S horizontally, that's all I'm doing. I'm not changing the direction of the vector if I apply the Möbius transformation. So this is already one type of orbit. Just horizontal lines parallel to the boundary, parallel to R. But then to get other orbits, I need to apply Möbius transformations to this type of orbit, and then I see the other orbits. So lines go to lines or to circles, and angles are preserved. So this line can go up or down if I push it by a diagonal element. So all these obviously are also orbits of the homocyclic flow. But if I take a more interesting Möbius transformation, then it will not go to a line, it will go to a circle, and angles are preserved. And since I'm sort of touching the boundary rather than intersecting it, so I need to have a circle that is tangential to the boundary, tangential to the real axis. And the arrows then point inwards. And the picture is that the arrows always point, if I follow the arrows, they point precisely along the geodesic flow to the point of tangency. That's the picture. All these arrows have to, in the hyperbolic world, point precisely to this point at the boundary. That's how, so if I start with some point in the hyperbolic plane and some vector, how do I draw the homocyclic orbit? I first look at the geodesic flow all the way to infinity, then I have a point at infinity. Then I draw the homocycle that goes through that point and touches the boundary at precisely the point where the geodesic hit, and that's the circle of points. And if I want to know the direction of this point, I have to again look at the angle that is the correct angle, so that the geodesic would again point to the same point. That's the rule, geometric rule, how to draw the homocycles and the tangent vectors at each point. Algebraically it's very easy, I multiply on the right by 1S01. Now, having said all of that, let me tell you why the generalization of Dani can't say the same thing. And let me talk again just about our favorite quotient by SL2Z. Take this point pointing north. Take the homocyclic orbit, it moves sideways, right? At some point it hits the boundary, and then the Möbius transformation hits it and moves it here, not changing the y coordinate, and it goes up. So that's a periodic orbit for the homocyclic orbit now, for the homocyclic flow. And you have not just one, you have many of them at various places. The most natural one would have been just starting with the reference vector. And algebraically that would have meant we take SL2Z and hit it with U. But U has an element, namely this one, which is in here. So if you start with the reference coset, or reference point in the homogeneous space we're looking at, and you flow in the horizontal direction at precisely time equals 1, you are back at that point. Because this coset equals SO2Z. And that corresponds to a loop. And that's this one. Now these are all very easy. There are others actually, namely these ones. Now you might say, well, that's not in the fundamental domain. Okay, then draw them in the fundamental domain, and if you follow them long enough, you will see that they goes out. So this periodic orbit is a periodic orbit which you can draw in the fundamental domain. But it's a longer periodic orbit because the period, the time, when you go from here to here in the hyperbolic world, it's actually much further away than here, right? Because of our 1 over y distortion. So this is a long periodic orbit, which if you draw it in the fundamental domain, looks complicated. If you take this vector and you draw it in the fundamental domain, it looks like this, and then you need to draw the circle, do many reflections, and after some amount of time, if you draw it carefully enough, it closes up. Okay, theorem for x equals SL2Z motion from SL to R. The holocycle flow has two types of ergodic invariant probability measures. Number one, the H measure. You can't deny that because it was here. And number two, periodic orbits, you can't deny that because they are here. Periodic orbit measures. You take the back measure sitting on the orbit, and then you normalize, you divide by the doped length so that it becomes a probability measure. And again, it's transitive action, so it must be an ergodic measure. Transitive action for almost every point. The points that are outside of the orbit of measure 0, they are irrelevant for this particular periodic orbit. So for this periodic orbit measure here, our space is conjugate to the circle rotation with continuous time on the one-dimensional circle. So it's very ergodic. So definitely these two types of measures, ergodic invariant measures, but the theorem says that's it. Those are the only ergodic invariant measures. Of course, there are also non-ergodic ones, like you can take the convex combination of the H measure and this periodic orbit. That's stupid. So let's not talk about non-ergodic measures. Always assume ergodicity. It's the right assumption. Okay. Now, I want to give you one more theorem that was actually proven before Dani. I think. Maybe not. I don't know. I'm always hazy.
Is this true for other triangle group?
Yes.
Instead of
Whenever you have a non-compact finite volume quotient, it needs to be bilattice, you have the same theorem. What changes is somehow every cusp gives rise to infinitely many periodic orbits with one periodic orbit of every length. Because the length of the periodic orbit is here in this picture precisely the height. It's one-to-one correspondence with the y-coordinate of the periodic orbit. So you can make the periodic orbit shorter by going up, or you can make them longer by going down. And you have a one-parameter family of periodic orbits. If you have two cusps, whatever that means, you would have two such families of periodic orbits. But it would still be that statement that your ergodic invariant probability measures are H measure, comma, periodic orbit measures. Theorem. That's Sarnak. Theorem by Sarnak. Let M index Y be the normalized probability measure, normalized invariant ergodic probability measure for the periodic orbit for y coordinate y. And again, I just stated for SL2Z, but the theorem is more general, it works for every lattice. Except if you have a complex quotient, then these things that I'm talking about now don't exist, so the theorem is true but empty. Then, the measures my escape to infinity, I'm not writing this down, escape to infinity when y goes to infinity. We see that in the picture, we don't need a theorem for that. Then the measures my equidistribute as y goes to 0, i.e. integral f dm y converges to integral f dm x. That's a different, that's capital, that's little, as y goes to 0 for every f in cc x. This time the cc is important. So let me say it in a different language, what this means. That means, look at all the ergodic invariant measures for the horocyclic flow. First look at all the invariant measures for the horocyclic flow. That's a convex complex subset, right, of the space of probability measures. Then look at the ergodic ones. Those are the extreme points of this convex complex subset. We saw this picture before. These were all probability measures, and these were the invariant probability measures, and then we had extremal points. And this theorem tells you the topology for the extremal points. And the topology for the extremal points is like this. You have a line of extremal points. Those are the various y coordinates. And at the place where y is equal to 0, that doesn't correspond in the family for to an ergodic measure. That's where the H measure sits. And here are the measures my, and on the other side it's open. The interval is open. That's the description of this set of extremal points for this. I got for this invariant measures for the horocyclic flow. Now let me tell you again without proof how that picture would have looked like for the geodesic flow and similar systems. You have this convex set, right? Convex complex subset. That's a very nice thing. There are lots of theorems about it. There's Krein-Milman, there's Choquet, there are nice theorems. But all of these theorems don't tell you how the set of extremal points really looks like. And the case of the geodesic flow is an example why all of these general theorems don't tell you how the set of extremal points looks like. Because for the geodesic flow, the set of extremal points, the set of ergodic measures, is actually dense inside the set of invariant measures. So it's very far from a nice picture like that. it's very anti-intuition, because our intuition comes from finite dimensions, and yeah. Good. Those are 3 theorems that I want to prove, and I think, yeah, I will manage in the second hour. And they all come from one and the same argument. Unless you look at the original proofs, then they are completely different. I mean, okay, those two are not so different maybe, because Dani really looked at Fürstenberg's work and then figured out how to generalize it to the non-compact case. And of course there was some work to be done, because the outcome is completely different from the previous case. And you work via harmonic functions, and it's quite a different story than compared to what I will do. And Sarnak, of course, yeah, he's a number theorist. He doesn't care about that statement, unless there would be an error rate attached to it. And so of course he proves an error rate as well, and he proves the best possible error rate, and it relates it all to spectral theory and to Eisenstein series. And it's again a completely different proof that I will not talk about, because it will take a bit longer. So I will use as an input mixing for the geodesic flow. So my aim is, and I will convince you that this is true, that all of these 3 theorems are corollaries of the mixing property for the geodesic flow, which we have established. And that argument also has a history of its own, and I think the first place where it appears, and maybe someone can contradict me if I'm saying something wrong, but I think the first place where it appears is Margulis's thesis. He uses this mixing argument and expansion to show an equidistribution of something, and use this for something else, but that's where this argument that I'm going to tell you appears, and later it then was used independently by Eskin and McMahon, again to prove some equidistribution results that then give you counting corollaries. So this has quite a history, this technique, and it's a very powerful thing, and it's not restricted to these cases. So I will try to prove it even more generally. At least in the compact case, I want to give you a more general theorem than Fürstenberg's theorem. And that generalization in the compact case comes completely for free. There's no slightly different language. So we suppose, because we leave behind SL2R because we want to make it more general, but other than that, that's somehow the very natural generalization with the same mixing argument proof. Suppose G is a nice Lie group. Lie is a simple Lie group, non-compact. I don't want to put too many statements there, e.g. SLVR, so at least it is more general than SL2, it goes to any SLV. Suppose gamma is a uniform lattice. Then how Moore theorem kicks in, and you have a finite volume quotient, x equal g mod gamma, and you have a normalized H measure, which is an invariant ergodic measure such that the action of any element whose powers go to infinity is mixing. Let A be diagonalizable, R diagonalizable. A and G be R diagonalizable. E.g. A equals e to the 2, e to the minus 1, e to the minus 1. Why not? Inside SM3. if we only have two entries, two particular numbers, then the group that I'm going to define next is a bit easier than if you use three different numbers, because then if you use three different numbers, you get the Heisenberg group, say, for SL3, and the Heisenberg group is not abelian, so you would have not abelian ergodic theorem, but the argument would work the same. But let's just think of a group like that, of this case, say, or something. Similar looking. That GA minus, that's the group that I want to define now, or maybe it's the other one. It could be this one, or it could be that one, depending on my luck. As luck has it, it's the other one. It's the group of all G and G for which A to the n, G, A to the minus n goes to identity as n goes to infinity. And we call that be the stable holospherical subgroup. So far I had setup and definitions theorem. Conclusion: the GA minus action is uniquely ergodic. And almost every orbit equidistributes as a corollary of the pointwise ergodic theorem. Yeah, no, it's corollary of the statement. Don't need a pointwise ergodic theorem for that. Okay, and these things we will prove after the break. Are there any immediate questions? Otherwise, you bring them with you. Ah, there's an immediate one.
Are they generalizable? What does it mean?
So I will, my Lie group is, say, a subgroup of SLDR. And then it makes perfect sense, right?
Yeah.
And if it's not a subgroup of SLDR, then let it act on the Lie algebra. Right? Any Lie group acts on its own Lie algebra, and this element should have the property that the induced action on the Lie algebra should have real eigenvalues.
Okay. So in the theorem, you don't need a G algebraic or something?
No. I only need that it's...
Otherwise you do it.
Yeah, I think I'm safe by the
Assuming that
assumption
you
that I have a
define-
lattice. The center will disappear because of the lattice. Let's just look at the linear group.
Yeah, because then you are linear
then
anyway.
it's always okay. Yeah. I agree. There are some technical things that I don't...
When do we continue?
we continue in half an hour, so it's 15:30. And I think I'm within the usual free extension. So, good. 75% of all n's, 75% of all n in n have greater or equal 75%, maybe it's 100%, I don't know. But greater or equal 75% of all n have x a 1 to the minus n in k. Well, this statement is defined, of course, by that limit expression, but that's nicer to say. And same thing for xu, right? xu is an x1. We get the same for xu a 1 to the minus n. It's also in k. Now, of course, the n's that have that statement here and the n's that have that statement here, these two sets of n's have nothing to do with each other. However, each of them is 75%, so for more than 50% of the time, both of the statements is true. So what was important about 3/4 is that it's bigger than 1/2. We get infinitely many, and that's the only thing we need, n with x a 1 to the minus n in k, x u a to 1 to the minus n simultaneously. And now we finish the proof with the stupid outline from yesterday. We have f of x. F of x equals f of x a 1 to the minus n. This holds almost everywhere, right? By assumption. So I'm not losing any epsilon or whatever. I'm not losing anything by saying this holds. I have to remove an alpha.
So logically you should have removed it before the final k. Yeah.
Now this is equal to that. And on the right I have the same thing here. This is equal to that. But now I'm rewriting this in a complicated fashion. And what I see here is something that goes to the identity rather quickly, exponentially fast. I still have my definition here. So if you multiply this with the minus here, with this, with the entry here, then this entry gets multiplied with this thing. And hence this is already small in the upper right corner, and then this fixes the diagonal entry and makes it even smaller in the upper right corner. But since this is now very close to the identity, and I'm in a compact set where I have uniform continuity, I can say that for large n this is almost the same. But since it's not changing along the way, it's the same all the way, all along. So we have shown this. To be precise, we have shown this for almost every x in x1 intersection x1 u inverse. Now you let epsilon go to 0 and you're done. You've shown it for almost every x. And then you do the same argument with n going to the other side for the opposite u. And you conclude that the function is invariant almost everywhere under all elements of SL2R. And because this is a transitive action, you conclude that the function is constant, and hence the theorem is proven. Are there any questions to this proof? Okay. So somehow these matrices with ones on the diagonal and something in one of the two corners, they keep popping up. They keep being part of the discussion. And yeah, they are interesting in their own right, and for most of what will follow, we will talk about them.